This is day 28 of Unit 7. We started today with a warm-up, so pause the video, take a moment, try the warm-up, then play to check your answers. So the first part asks us to graph y equals the log base 4 of x. So remember from yesterday, you need to put that into exponential form, so 4 to the y equals x. So I can make a table, and when I make the table, I'm going to input y values rather than x and get the outputs for x. So when I do that, 4 to the negative 1 is 1/4, and 4 to the 0 is 1, and 4 to the 1 is 4. So I can graph those. So just get some points on here. So 1/4 negative 1 is right about there. 1, 0 is right there, and 4, 1 is right there. So I'm going to go ahead and connect those points, and I know if I get closer, it's just going to keep getting closer to the y-axis. So there is a horizontal asymptote at x equals, or I'm sorry, vertical asymptote at x equals 0, and the locator point is 1, 0. So there's our original graph. That's y equals log base 4 of x. So now I'm going to go ahead and reverse those points to get the inverse graph. So negative 1, 1/4, 0 and 1, and 1 and 4. So negative 1, 1/4 right there, 0 and 1 right there, and 1, 4 right there. So now I have that graph. So we know that that has a horizontal asymptote, because it's exponential, at y equals 0. And that is our inverse graph, which right now we know is, well, actually, let's get the equation and then I'll label it. So find its inverse equation. So I'm going to use my 4 to the y equals x. I put the log in exponential form, and then I just need to interchange my x with y. So 4 to the x equals y. Y equals 4 to the x is our inverse equation. So that's what we graphed here. And if you check that, if you figure out the table for y equals 4 to the x, it should match with what we just got from flipping the points and graphing. You should end up with that graph and this table here. Okay. That's the original table. Okay, so that's our warm-up. All right, so today we started by, well, first of all, I think we were finishing this up from yesterday. I think we already had done that one, plus that's what we just did in the warm-up. So let's start with this one. We want to graph that, and this you just want to put in your notebook. So in order for me to graph this, I can't put this in exponential form. What I want to do instead is think about my table for the most basic log, which is this one, log base 4 of x. So I'm going to use that table. And again, we just put this in exponential form to get that. And then remember, we had 1/4 here, we had 1, and we had 4. So I'm going to use that table, and I'm going to adjust that table to give me the table for this equation. So minus 4 and plus 1, we know based on all the other shifts we've learned all year that subtracting 4 from the x is right 4, and adding 1 is up 4. So if I go to the right 4, that's increasing the x by 4. And if I am going up 1, that's increasing the y by 1. So I just put a plus 4 and a plus 1 over the x and y columns. That's going to help me get my new table. So I'm going to add 4 onto 1/4 to get 4 and 1/4. I'm going to add 1 onto negative 1 to get 0. I'm going to add 1 onto 4 to get 5, and 0 onto 1 to get 1. And 4 onto 4 to get 8, and 1 onto 1 to get 2. So there's my new table. I also know the original has a vertical asymptote at x equals 0. So if we shift that 4 to the right, think about that, that would take it to x equals 4. So I'm going to go ahead and plot, make yourself a coordinate plane. Let's go ahead and plot x equals 4. And label it. And then let's plot those points. So 4 1/4, 0. So just a little bit past 4. 5, 1. And lastly, 8, 2. right there. And we have enough points that we can draw in our curve and getting really, really close to that vertical asymptote. And there's our graph. We have our asymptote drawn and labeled. The only thing we need would be the locator point. Remember, 1, 0 was the locator point, so that would now be 5, 1 after we shifted it. So that's the point that you need to label. That's it. That's our graph. Okay, so next we worked on page 29, problem number 1. So let's try that. So looking at this equation, I can see that I want to think about y equals log base 6 of x. That's the most basic before it's been shifted. So let's put that in exponential form, 6 to the y equals x, and let's make a table for that. Now, it doesn't say I have to graph that. I'm just using this table to help me get the table for my graph. So I'm going to input the y's, and I'm going to get the corresponding outputs. So 6 to the negative 1 is 1, 6, 6 to the 0 is 1, and 6 to the 1 is 6. So I'm going to plot those points. Actually, I'm not going to plot those. Remember, I'm just going to use them to get my new table. So I'm looking at the equation, minus 1 and minus 5. We know that's right 1 and up 5. So right 1 means we're going to increase by 1. Actually, I should put this here, I guess. Increase by 1 and subtract 5. Whoops, I didn't mean, oh my goodness, I didn't mean up 5. I meant down 5. It's minus. Okay, so right 1 and down 5, which would be plus 1 and minus 5. There we go. Now we have it. So we're going to add 1 to 1, 6, getting 1 and 1, 6. We're going to add negative 5 to negative 1 to get negative 6. 1 to 1 to get 2, and 0 to negative 5 to get negative 5. And then 6 to 1 to get 7, and 1 to negative 5 to get negative 4. We know that the vertical asymptote was x equals 0, but it's been shifted 1 to the right, so that takes me to x equals 1. So go ahead and plot x equals 1 as your vertical asymptote. And go ahead and plot the points. So 1 and 1, 6, negative 6. 2, negative 5. And 7, negative 4. And now I have those 3 points, and I have the vertical asymptote. And I'm going to figure out which one's the locator. That was 1, 0, so that's the 2, negative 5 right here. That's the locator point. So there's our graph. Now the only other thing we need to do is to state the domain and range. So domain looking left to right. I'm going to use interval notation, but inequality is fine. I can see that 1 is where it starts and that it goes to infinity, and parentheses for both because it doesn't equal 1 or infinity. Range, negative infinity to positive infinity, both with parentheses. If you use the other notation, it would be that. And it would be that. Okay. All right, next thing we did was we took a look at this problem. So go ahead and copy that into your notes. So remember, we just really need the important details. So in this problem, the important details are that we start with $2,000. We are compounding this money quarterly. The annual rate's 5%, and that we want to know how long till we'll have $3,000 in the account. Okay, so once you have all that copied, let's go ahead and start the problem. So hopefully you can remember, we need to get the multiplier first. So we're going to take, remember when it's compounded, something other than annually, you have to divide the rate. I'm going to get it as a percent first. I'm going to divide that by the number of times it's compounded per year, which is 4. I'm going to add that to 1. That number is my multiplier. I'm going to take that multiplier times the initial amount, and I'm going to raise that to the x. And when I do that, that equals y. So there's my basic equation. So now I know that y is going to be 3,000 because that's the amount I want it to equal. And again, 2,000 is my initial amount. You're going to figure out what 1 plus 0.05 divided by 4 is. If it's a repeating decimal, you're going to leave it exact. This one actually ends up being 1.0125, so that's not too bad. So I'm going to write the decimal form of that, and that's raised to the x. So that's what I have so far. I notice I need to solve this for x, so I'm going to divide both sides by 2,000. 3,000 divided by 2,000 is 3 halves. 3 halves is 1.5. So I have 1.0125 raised to the x. Now, we did these problems earlier in the unit, and when we got to this step, remember we guessed and checked because we didn't know how to solve algebraically yet. Now we know how to solve algebraically. So we know that we need to take the log of both sides of this equation. And that allows us to use the power property and bring that x down front. So I have log of 1.5 equals x times the log of 1.0125. I'm trying to get x by itself, so I'm going to divide both sides by the log of 1.0125. So normally we would get the exact answer, which is what that we have here on the left, and the decimal approximation. Here I care more about the decimal approximation because I'm trying to answer this word problem. So I'm going to go ahead and type that in the calculator and figure out what I'm getting for x. So go ahead and try that. So when we type that in, what are we getting here? Not sure if I have that. Let me see here. Oh, here we go. I'm getting 32.64. Now, keep in mind, x represents whatever the units are that were for the multiplier, which is quarters. So that's number of quarters. So I asked for years, meaning you need to take that answer and divide by 4, which gives us approximately 8.16 years. And that's your answer. Okay. Next, we did on page 31, we did problem number 2. So we have Barnaby's grandfather. He's always complaining that back when he was a kid, he used to be able to buy his girlfriend dinner for only $1.50, and that was 60 years ago. So if that same dinner now costs $25.25 and the rate of inflation has not changed over the years, write an equation that will give you the costs at different times. So do we know the initial amount? Yes, we do. It's 1.5. Do we know the multiplier? No, so let's use a variable for the multiplier. Do we know the time? Yes, that was 60 years ago, so that's our time. And we do know that after 60 years, the meal now costs $25.25. So that's those are your first couple steps. Now we're trying to solve for m, so we're going to divide both sides by 1.5. When you do that, this comes out to be a non-terminating decimal. It's a repeating decimal. So I don't want to round. I want to just leave it exact. So I'm just going to leave it as 25 over 1.5. So I'm trying to solve this. Now, think carefully here. I know recently we've done a lot with logarithms. Not every problem involves logarithms. This one does not. Why? Because I'm trying to solve for m. M is not the variable exponent. It's just a variable base. So if it was a variable exponent, then I would use logarithms. But this is a base. So I'm trying to undo the 60th power, which means I want the 60th root. Be careful with that. Common student mistake, I think you have log on the brain right now. Common student mistake is to just take log of everything. We don't want logs here. So the 60th root of m to the 60th is technically the absolute value of m. Now in this particular problem, we actually don't care about the negative, so we just kind of drop it. I'm still going to write it though for now, because multipliers can't be negative. So we have the 60th root of 25 divided by 1.5. That's not a nice number, so that's why I left it exact rather than rounding. So I have plus or minus that number. Again, I'm not rounding that. I'm leaving it exact. Okay, so next I'm supposed to write the equation. Well, my equation is y equals 1.5 is the initial amount. That number is my multiplier. Again, I'm dropping the negative 1. And that's raised to the x power. Here, x is the number of years. So that's A's answer. Okay, next part is B. So B says, use your equation from part A to answer the question, how many years ago was that dinner worth $20? So hopefully you're realizing you want to substitute 20 in for y. Okay, I don't know x. So I'm going to first divide by 1.5. That comes out repeating, so I'm going to leave it exact, not round it. Okay, so next I see that I have a variable exponent. So this is exponential, which means I do want to take the log of both sides on this one. Variable exponent solving, you want to take the log of both sides, which allows me to bring the x down. And after I bring that x down, then I can divide both sides by the log of the 60th root of 2525 over 1.5. And of course, we're getting to the bottom of the screen and it always decides it wants to stop working. Okay, so now that I've done that, I'm getting x is approximately, I'm going to type that in the calculator, and I should get 55.05, and remember these are years. Now, let's think about what that answer means. That means the years since dinner was $1.50. But my question was how many years ago, not how many years since dinner was $1.50. So I'm just going to write that years since $1.50 price. So now think about it. If the $1.50 price was 60 years ago, and this was 55 years since the $1.50 price, we need to figure out how many years ago. So we need to subtract the 60 years ago minus the 55.05 years since it was $1.50, and that will tell me that 4.95 is the approximate number of years ago, which is the answer to the question. Okay, so a couple things to be careful with. First of all, when you have repeating decimals or non-terminating decimals, make sure that you use exact and don't round to the very, very end. Notice I kept it all exact till the very end. That's when I rounded. Secondly, when you're solving exponential equations, remember, you're going to use logarithms, take log of both sides to solve if it's a variable exponent. But if it's something where we know the exponent, and the variables like the multiplier or one of the other numbers, you are not using logarithms to solve, only if the exponent or the variable is an exponent. Okay, so your assignment for tomorrow, I'd like you to complete 29 to 30 problems 1 to 8. We actually did number 1 together a moment ago, so 2 to 8. And 31 and 32, I'm going to change this a little bit. You're going to do just problems 1 to 4, and we just did number 2 together. So 1, 3, and 4 on pages 31 and 32. 1, 3, and 4 on pages 29 and 30, problems 2 through 8, because we just did number 1. So do those for tomorrow. Reminder, you have a test coming up at the end of this week, and your packet will be due as well.